Hello, I'm Kathleen Coleman, and this is Lab 2 for Physics 2211, the Falling Object Lab. So the purpose of this experiment was to track the motion of an object as it is dropped from rest and as it experiences free fall, and then to use that to see how well a model of motion that uses only the force of gravity compares to a model of motion that uses both the force of gravity and drag force. So we have three graphs to look at: our experimental graph, our computational model graph with only gravity, and then our computational model with gravity and drag. The physics principles we need to understand for this lab are Newton's second law, which says that the final velocity equals initial velocity plus F net over m times delta t, the position update formula, which says that the final position equals the initial position plus velocity times time, weight force equals negative mg in the y direction, and then drag force equals b times v squared in the y direction, where b is a drag coefficient. And then I also have here a free body diagram just showing the forces we have going on. And then I have a little sneak peek to the end of the lab where we can see that the gravity and drag model does do a better job of predicting the motion of the experiment. This is the video from Tracker. We can see the system, which is the stuffed animal, and then the surroundings, which is everything else. And here we have the code for the model that only includes gravity. So the mass of the ball was 0.185 kilograms. The final time was 0.733 seconds. The initial position was 0, 0, 0. The initial velocity was 0, 0, 0 because it started from rest. The proportionality constant is b because we are not considering drag force at this time. The weight is minus the mass of the ball times g, and then the drag force is basically just b times the velocity squared, but in this case, because we're multiplying by 0, it'll be 0. And then we use Newton's second law to find the final velocity, and then the position update formula to find the final position. And then we also have our arrow scale going on. So the way I found the arrow scale was I did mg and then did 2 divided by mg. So in that case, in my case, it was 1.1031, and that scales it correctly so that our arrows are more meaningful. So you can see for the gravity model in our little arrow diagram, we only have weight. There's no drag force. And our position versus time is concave down, and our velocity versus time is just linear. For the gravity and drag model, our code will be very, very similar to the gravity model. The only thing that changes is that b will now be 0.119, which is the proportionality constant that I found for my situation. So for the gravity and drag model, we have the little arrow diagram. We have weight, but then we also have the drag force. The position versus time diagram will still be concave down, but now instead of our velocity versus time graph being linear, it will be concave up. If we look at our graph that includes our experimental data, our gravity model data, and also our gravity and drag model data, we can see that the computational model that includes both gravity and drag does a better job of matching the experimental data, which makes sense because in real life, which is where our experiment took place, the air does have an effect. And it makes sense that in the gravity model, it would go further than it would in the gravity and drag model, because in the gravity model, it doesn't have that upward force, but in the gravity and drag model, it does. And some possible sources of error are human error in picking points on tracker, not dropping the object straight down, and the camera being angled. Only the model with drag predicts the terminal velocity because we can see the velocity versus time graph flatten out, and it will eventually reach a limit. If you threw the object straight down at the beginning instead of it starting from rest, the terminal velocity will be the same. The object will just take less time to get to that terminal velocity, which we can see from this graph and if we compare it to the one on the previous slide. Thank you.